Welcome everyone to our final afternoon of the first Spec Q-Bar. I'm Dave Swinarski. I'm the chair of the math department at Fordham University, and it's my pleasure to introduce Kevin Tucker. I think Renzo expressly asked me to moderate this afternoon so that I could tell an embarrassing story about Kevin. That's not going to tell a nice one. Kevin helped me make a good first impression on my father-in-law. I went to visit Kevin several years ago in Utah with his postdoc there. And I was reading a book by an author named Rex Stout, and the main character was a detective named Nero Wolfe. And then I said, I think you'll really like this book. So when I went home, I went and read that book and all the others. There's about 40 in total. So Nero Wolfe is meant to be something like an American Sherlock Holmes. Anyway, flash forward a couple of years, started dating husband Bill. And when I went to his apartment for the first time, I realized he had read self-released books. I'm like, oh, that's amazing. I've read them all too. And when we started dating a little bit more seriously, and he told his parents for the first time that he wanted to bring his new boyfriend home, he told his father, who's a retired civil engineer, oh, my boyfriend is a math professor, and he's read all the Nero Wolfe books. And my father-in-law said, I want to meet this. So, read anything that Kevin recommends. And with that, take it away, Kevin. You'll be telling us about recent advances on two variants of the F signature.
Okay, well, thank you very much for the introduction. Can everyone hear me okay? Okay, good. So if you can't hear me or understand what I say at some point, please let me know. My handwriting is also okay, hopefully, but it does tend to go in and out of legibility at times too, so please speak up if you can't follow. All right, so I have a lot to tell you today. I'm not going to really assume too much background here, but there will be some segments of the talk that are aimed at a higher level audience, and some are aimed at people who are less familiar with a lot of the things I'm talking about. So don't feel free to zone in and out as you see fit on this last afternoon. All right, so let me put the following setup for most of the talk. Right, so I'm going to look at sort of as a standard setting, a nice Noetherian local ring. And I really mean nice, right? So to me at least, rings can be very difficult objects to work with at times. So I'll give you a good example to keep in mind, but for the experts, I'm thinking of something like an excellent local ring, right? So, let me make two other assumptions. So I'm going to let D be the dimension of the ring, right? And also I want to assume that the residue field is perfect, and that's in part because I am going to switch the characteristic of the ring at times throughout the talk, but for, I would say, the first 2/3 at least, I'm going to work in characteristic P, right? So, and to try and let you know when I'm working in characteristic P, I'll write that just by saying that the field FP is a subring of R, all right? All right, so as I said, I want you to have an example ring in mind, and so this is the kind of ring I want you to think about for most of the first part. All right, so here, let's say, just take a power series ring over FP and kill a bunch of equations. Okay, so I want to tell you about a numerical invariant of singularities called the F signature, and specifically two very recent variants on it, right? So, but for the most part, the first part of the talk will just be a little bit of background information on the F signature, right? So to do that, I have to first tell you about the F splitting numbers of the ring, right? So since I'm working in characteristic P, the machine that drives everything is the Frobenius endomorphism, or Pth power map, right? And because it's an endomorphism, right, so the real power comes in doing it as many times as you like. So take a look at the iterates of Frobenius. Oh, another sort of standing assumption, all my rings will be domains for the most part as well, right? So in order to tell you a little bit about the F-splitting numbers, I want to give you another way to picture and think about the Frobenius endomorphism. Namely, I can view the p to the eth power map in a different way, namely as the inclusion of R in its ring of p to the eth roots. Right, so you're probably familiar with the freshman's dream over here on this side, that the sum of pth powers is the pth power of the sum, right? And that's how Frobenius works. Here, same thing. Every element of R inside of, say, an algebraic closure of its fraction field has a unique p to the eth root, and the sum of p to the eth roots is the p to the eth root of the sum, right? So that gives me a ring abstractly isomorphic to R, right? And I can identify the usual Frobenius with just the natural inclusion of R in its ring of p to the eth roots, okay? All right, so a lot of information comes out of studying. Right, so one more comment. So on this side, one of the reasons I do this switch is the power of Frobenius is that I can do it over and over again, but of course the source and target are the same. But for those of us that have problems telling left from right, I prefer this picture because at least the right side looks different from the left one. Right, so a lot of the power here comes in studying these gadgets R1 over p to the e and thinking about them as R modules and looking for what structure they have. Right, so here's the definition of the splitting numbers. Right, so take R1 over p to the e and think about it as an R module. What I want to try to do is then decompose it and split off as many copies of R as I can. So decompose it into some free part and something else, right, where you can't take any more. So there's no more R's inside of this module M sub e. Okay, is everyone happy with the description here? All right, so if your ring is complete, like in my example case here, then our modules satisfy Kroll-Schmidt. So this is a unique way to do this. There's no ambiguity about what the number AE is. Otherwise, even if the ring's not complete, it's pretty easy to show that the number of copies you can do this in any way of decomposing gives you the same thing, right? And this number here is called the eth F splitting number of the ring R. Okay, and so the first sort of objects here I want to study are these F splitting numbers. The ring R is F split if there's at least one copy that comes out, right? And so there's a long history of the study of Frobenius splittings dating back at least to the 70s, right? Both in sort of local settings and in global settings. They arose globally in the study of representation theory and locally in my contacts by Hoxter and Roberts and some others, right? So, but there's a lot of information encoded sort of in these numbers. All right, so as I said, the F signature is going to be invariant of singularities. And so there's sort of a motivating theorem that explains, at least to me, why these numbers can be used to think about and study the singularities of the ring. And that theorem is due to Kunz. And what he showed was, well, the following things are equivalent. Right, so first, R is regular. Right? Or equivalently, the eth splitting number is equal to p to the ed for some e. Right? Or equivalently, same thing. Right? If it's true for one e, it's true for all e as well. Okay? Right? So and in general, this p to the ed here is the rank of R1 over p to the e as an R module, right? So that also tells us sort of how big these numbers can be. What was that? P to the e times d. for some iterative Frobenius. D is the dimension, and it's fixed, yeah. All right. All right, so of course the ring to keep in mind here, all right, is what this looks like for, say, the polynomial ring itself here, right? In each case, this ring R1 over P to the E, or this module R1 over P to the E, is the same thing as just, well, it's again a power series ring over Fp, where the variables are the P to the E roots of the original set of variables, okay? But the key point here is that this and this really is then a free R module. And it's explicit to write down a basis, namely look at the set of all the monomials. Right, well, okay, so these exponents, the alpha i's, are some monomials in the roots of the variables. And if ever you have something that's bigger than 1, I can split off some R module relation. Right, so you just count these up and they're P to the ED of those, and that gives you the rank of this thing, and also computes and shows Kunz's theorem here explicitly. All right, so this is sort of the easy direction of Kunz's theorem, if you will. Is everyone happy with this? All right, great. Okay, so as I said, I want to sort of look at these Frobenius splitting numbers. So let me look at some examples here first. Right, so all of my examples here on this board are going to be quotients of a power series ring in 3 variables. Let's do this. Mod some single equation, right? So here in the regular case, we saw an example where the Frobenius splitting numbers were P to the ED, right, for each E. Right, so here's something where it's slightly less than that. Right, so if you take the cone over the smooth quadric here, right, so you can show that the Frobenius splitting numbers are the roundup of P to the 2E over 2. Right, so, okay, so pretend you're not in characteristic 2 for a second, because that's just odd. So if P is odd, right, then this is just P to the 2E plus 1 over 2. Okay, great. But if you tweak the equation just a little bit, right, so this equation is what's known as the Whitney umbrella, if you're familiar with this. So again, imagine taking a piece of paper and folding it over and doubling up on a line, right? So you can show that the splitting numbers here, well, again, there's 2 cases, right? So the first is if you're not in characteristic 2, so in characteristic 2, the numbers are always 0, right? But if you're not in characteristic 2, then you get the roundup of P to the E over 2. All right, so what I want you to see here is, well, this can really depend on the characteristic, right? And second, the ring here has dimension 2, right? So the growth rate of these numbers is now different from what it was in the regular case or in the first example, right? Third example. Let's say I take the Fermat cubic, right? So you can show, well, the splitting numbers are 1 for each E if P is equivalent mod 3 to is 1 mod 3, right? And it's 0 otherwise, right? So again, for those of you who have a stronger number theory background, this example jumps out at you as saying, oh, there's something else going on here, right? So this, okay, so all of these things should have pictures. This thing kind of looks like, you know, whatever that is, okay, fine. And this one we talked about the airplane, the paper, paper folded over in half. And this thing is walk down the street, go to Tim Hortons, pick out a donut, and take a bunch of lines and stick over it, and it's the cone over that thing. All right. So more generally, if I take a cone over an elliptic curve, in its ordinary, you get 1, and if it's super singular, you get 0. Right. Similar statements hold for cones over abelian surfaces, and it's embarrassing that the number theorists can't show me that I get infinitely many 1s for an abelian threefold or higher. All right. So. And just to add to my examples one more, if I take this equation and tweak it just a little bit, change 3 to 4 or any bigger number, you'll get 0 forevermore.
How can r to the 1 over p to the billion in example 4 have no rank?
It has no free sum end. So for example, even in this case, the point here, maybe this will say it a little bit better, is in this case you get sort of the unique, this is related to T's classification of vector bundles on elliptic curves, and this is related to the existence of a unique indecomposable vector bundle of a given rank. Free sum ends, exactly. Literally free. Not locally free. I'm working locally. I'm working at the cone point. Yeah, absolutely. Any other questions? Yeah, it means that if you write R, take this as an R module and try to decompose it as a direct sum of other R modules. There's no way to split off another free sum end. So another way of saying this, let me put it, let me say it one other way. Right, so maybe this will make it more clear. Right? So this is the largest integer n, so that there exists an R module surjection from this onto a free module of rank n. Right? Once you have such a thing, of course, since this is free, it'll split off, right? But this shows, this is another way of presenting it that's independent of any decompositions or choices of things like that. Okay? All right. Okay, so let me do the first big definition here then. Right, so the first definition slash theorem, and this is due to Hunicke and Lusky. Right, so building on work of Smith and Vandenberg. Right, so the F signature is the following limit. So you take a limit as e goes to infinity of the e splitting number of R divided by p to the ed. Okay, so we have a bunch of examples here sort of on the board. Of course, here in the regular ring case, you see that the signature is 1, and in fact, you are naturally led to think about this limit. You're really comparing what the splitting numbers are, what they would have been for a regular ring of the same dimension. So this is sort of some asymptotic measure of how singular your ring is from this perspective, or how far these modules R1 over p to the E are from being free. Okay, so the same thing over here. So here we see this ring here, divide by p to the 2e, take a limit. I'll get 1/2, so this is half as regular as a regular ring is, if you like. Over here now, no matter what the characteristic is, even though it depends, the F signature is 0 because the growth rate was not maximal anymore, right? And the same thing holds, of course, going all the way down. Okay, is everyone happy with that? All right, so what's not clear at all from this presentation here is that this limit exists. And that's at least in full generality that's true to me. All right. Let me add one other result as well. There were two proofs that came out at about the same time. One due to Thomas Polstra and another that we incorporated into a joint paper, right? This gives a lower semi-continuous numerical function on ring spectra in prime characteristic, right? All right, so really what's that saying? So the F signature, I want you to think about it as some kind of a measure of singularities. It's 1 if you're regular, and if you're not regular, it's smaller. And saying that you're lower semi-continuous roughly is saying here that it can get smaller on closed subsets. So for example, the locus where it's 1 is going to be some open set, because I have a nice ring, right? And then the singular locus, some closed set, is where it's going to drop. Okay? Everyone happy with this? All right, so let's do this one. Another set of examples. Same setup. Same problem. And let me avoid some problems in low characteristic. Oh my goodness. So some of my favorite singularities, right, are the so-called rational double points or Duval singularities. And so those are nice hypersurfaces that are determined. Yeah. I will lift it up at the end. Give me a sec. All right. Okay. So there's a bunch of equations. I can write the first one down. It actually sort of appeared on our first list. Right, so they have a standard set of standard equational forms, and they're listed according to these Dinkin diagram types due to the Makar correspondence. So if you look at the dual graphs of the minimal resolutions, and we've already seen dual graphs in some of our previous talks, those dual graphs correspond to trees of P1s in the corresponding Dinkin diagram configuration for each of these types. Okay, so all of these have something with F signatures computed. Let me write them all in red here. Right, so for the ANs, I get 1 over n plus 1, dn 1 over 4n minus 2, 1 over 24, 1 over 48, and 1 over 120. So again, I don't put this up here just at random. So if you're more familiar with these things, each of these singularities is a finite quotient singularity over the complex numbers. And in fact, the denominator of each of these things is the order of the corresponding, well, cyclic or binary dihedral or tetrahedral, octahedral, or icosahedral groups that give the corresponding singularities, right? So just another indication that there is some geometry and information that's really being encoded by these numbers. Okay? Is everyone happy with this? Okay, great. So, oh yeah. Great. So as I said, the difficult thing here, oh, you're right. So the important equation I want you to remember for later is x squared plus y cubed plus z to the fifth was the E8 down here. Yeah, in the back. Yep, and we'll say a little bit about that. It's not true in general, right? So give me a little time to say about that, but it is related to the fact that these are all nice finite quotient singularities. All right, so just building up a little bit more, let me say that the hard thing here I'm trying to emphasize is that it was not clear that these limits existed. So let me give you an example which kind of hammers that home. All right, so in all of our examples over here, what you ended up with was essentially something that looks like some sort of polynomial with maybe rational coefficients in p to the e. And that's just not true in general, right? So Hahn and Monsky showed right, if you look at 5 variables in characteristic 3 and take the sum of the squares, right, they were able to compute all of the splitting numbers, and they got the following. Right, so the dimension here is 4, so I get something which starts off looking like a polynomial in 3 to the e, right, and ends up with something that's not related to 3 to the e, right? So in fact, our paper is called Some Surprising Hilbert-Kunz Functions, right, and is related to something we'll talk about a little bit later on. Okay, even worse. Monsky has a different conjecture. So if you look at the ring right, so 5 variables, but let me give them actual names this time, x, y, z, u, v. What I'm going to do is take a certain singular cubic and try to smooth it out in some way with the new variables. Right? So Monsky conjectured here that the F signature is 2/3 plus 5 over 14 root 7. Okay? And at this point, it remains an open problem whether this number can be rational or irrational. All right? So what kind of values this thing can take. Okay? Monsky's conjecture is, or he has a series of conjectures in this paper I'm referring to, many of which are really related to this singular cubic over here. And really what he was studying is a related invariant, which I want to tell you about next, called the Hilbert-Kunz multiplicity, right? And so that invariant, which I'll denote EHK, is related, and he conjectures in the same paper then that limit is something very similar, right? Also some quadratic irrational. right? But let me say that if Monsky's full package of conjectures here was true, then you should also expect that you can get transcendental numbers here as the values, okay? Moreover, sort of for cardinality reasons about the corresponding rings we're taking quotients of, at the same time, it's expected that the set of values, if you say work over FP bar as your coefficient field, should only be countable. So you have an interesting set of countable real numbers to be working with, okay? In any case, the key point here is that this thing is really not a polynomial in p to the e at all, right? So the limits in their existence is not obvious. And that we really have no idea exactly what's going on in the limits at this point. And the fact that all those numbers look nice is not something I sort of expect in general. Yeah. So what Monsky really does is he makes conjectures about the Hilbert-Kunz function for powers of the singular cubic, and then he has a bunch of combinatorial tricks to extract out either algebraic irrational or transcendental irrationals related to what those things are. So I think he has an explicit conjecture of what it should be. I don't think there's any, I got nothing for you. Totally the Wild West. Okay. Okay, so with that, let me tell you, don't look at my cheat board, right, about what Monsky was really conjecturing about. Right, so Monsky was really working with the Hilbert-Kunz multiplicity. Right, so what is that? Well, the Hilbert-Kunz multiplicity of some ideal I is given by the following limit, which again looks like an F signature type limit. Right, so, all right, so what are the inputs? Well, this you should think of as a variant of Hilbert-Samuel multiplicity. So the input is I have to give you a finite co-length ideal to start off with. Feel free to take the maximal ideal, that's fine to think about, right? And what you do is you sort of take what you would normally do for the Hilbert-Samuel multiplicity, not up to the rescaling in terms of d factorial, but just forget about that for a second. And instead of putting in the regular powers of the ideal, you put in the so-called Frobenius or bracket powers, which is just the ideal you get by expansion of I under the eth iterator Frobenius, right? So in other words, it's the ideal generated by all pure p to the eth powers of elements of the original ideal, okay? All right, so I said the Hilbert-Kunz multiplicity and reference Monsky. So the theorem here again is that the limit exists, right? There's a standard story to tell here. One of the interesting things here is why is Kunz name? Well, we saw his name in the characterization of regularity earlier, but Kunz actually has a paper saying that the limit doesn't exist. So he has an invariant named after him despite arguing that these limits don't exist. Later, independently, Monsky says that he was working on some things in Iwasawa theory, came up with a general argument that such limits do exist, showed Eisenbud, who told him that Kunz said he was wrong, right? And that is the story sort of how Kunz got his name attached to an invariant that he claimed does not exist. Hochster says that one way to get around this is to instead refer to this as the Hilbert-Kunz multiplicity, okay? But again, very similar to the limit above, this thing here, it's not clear that these limits exist. These numbers are not polynomial in p to the e, and I expect sort of similar behavior in terms of what values they can take on, right? But more than that, it's a high-level theorem of Monsky and Brenner at this point that there does exist a ring with an irrational Hilbert-Kunz, right? Now, the example is not constructive, so I can't really bootstrap off it to get anything else, but we know that a related invariance like this can be irrational. Okay? All right, and again, both of these things really are measures of singularity. Right, so Watanabe and Yoshida show that the Hilbert-Kunz multiplicity of the ring, or of the maximal ideal, is what I mean here, is, well, this is bigger than or equal to 1, with equality if and only if the ring is regular. Right, and in the similar vein, Hunicke and Lusky, who defines the F signature limits in the first place, show the same statement, at least flipped around, for the F signature instead. Okay. All right. So, like I said, the title of the talk was to try and tell you a little bit about two new recent variants on the F signature. So let me sort of move towards that. But I have to motivate it in some way first. Right, so to motivate the first sort of variant I want to tell you about, I want to tell you another really high-level theorem. Right, due to Smith, Hara, and Mehta Srinivas. Right, so what they showed is if you take a complex algebraic variety and you go through standard sort of reduction to positive characteristic techniques, right? So imagine your variety is defined by equations with integer coefficients, naively if you like, and just go mod p for all of those equations. You can think about getting an arithmetic family of varieties in positive characteristic, right? And what they showed was that if x has some mildness assumptions, so if you know what Q-Gorenstein is, great. If not, think Gorenstein or don't worry too much about it for now, right? They showed that you can take certain important singularity classes appearing in the minimal model program in characteristic 0 and test for them right? By looking at certain corresponding singularity classes in positive characteristic, right? So in other words, to try and do this as quickly as possible, my motivation here, and one of the ways I think about singularities in the first place, is via this reduction to characteristic P bridge, right? Taking certain singularity classes in characteristic 0 and trying to find their positive characteristic shadows, right? So here for the F signature, the relevant one is log terminal or KLT singularities. And what the theorem says is that that singularity class you can check for by looking at a certain class of singularities in positive characteristic called F regular or strongly F regular singularities, Okay? And to link this back up to the F signature, we have a theorem of Auerbach and Lusky, right? And so what they showed is that in positive characteristic, right? So again, right? So in positive characteristic, right? So the F signature is positive if and only if the ring is strongly F regular. Okay? All right, so in other words, they identified the sort of class of singularities from a different perspective for which this invariant is an interesting number, is positive. All right? Right? And to tell you about the first variant, what I want to tell you about is something that people have been working on for about 10 years, which is, well, can you do some similar things for other numerical invariants for some of the other important singularity classes? So in particular, if you look at rational singularities, the analog and positive characteristic are F rational singularities. In fact, I could write the same theorem here with rational and F rational, and it's due to exactly the same people. Okay. And the question is, can you define, or people have been trying to define, an F signature-like invariant that will measure F rational singularities instead? Okay. All right. So let me tell you the following definition. All right. So, okay. Right, so all right, so let me add to my assumptions just a little bit. I'm going to assume that R is co-Macaulay with a dualizing module, right? So who here is happy if I say the words co-Macaulay? All right, so most of the room. If you're not, let me just tell you a quote from Hochster. He says, "Life is really worth living in an Arthurian ring when all the local rings have the property that every system of parameters is an R sequence. Such a ring is called the Cohn-Macaulay ring." Right? So roughly speaking, again, I'm just adding to the niceness properties of the ring, but in my mind, almost all rings that I like are Cohn-Macaulay. Right? So in particular, any hypersurfaces. All right, so the definition here is we're going to do something very similar to the F signature, namely look at the canonical module for the ring 1 over P to the E, right? And ask again, what's the largest number of copies that you can surject onto for direct sums of omega instead of for the original ring R, right? So this thing here should be as big as possible. Right? And again, you're sort of naturally led to consider such things if you just take Frobenius splittings like you had for the F signature and hom into omega. You take sort of the Grothendieck dual of that sort of setup. Okay? So his definition, of course, was that the dual F signature right? So do a very similar thing. Take this thing and divide by P to the ED, right? And try to take a limit. And the first theorem I have for you today right, is that once again, we can show this limit exists. Right? And people have been trying to do this for 6 or 7 years now. And this just went up on the archive probably about 2 weeks ago. All right, so very recent. Okay. One of the big differences with the F signature is whereas for the F signature I had a lot of explicit examples with the full computations to give you, it's very hard to actually get your numbers, your hands on these numbers at all, right? So in particular, I still don't know even the exact computation of the BEs, even in the toric cases, right? Of course, if your ring is Gorenstein, which is the same as saying here that omega r is equal to r, this gives you back the F signature on the nose, and I still have all of those examples, right? But more generally, I really don't have anything like that, okay? All right. So again, sort of what's the punchline here? Punchline is the first variant is if you're looking at things through the lens of reduction to positive characteristic, right? You could ask similar questions and try to find other related invariants that would test for various things like this, okay? All right, so and the last one I want to tell you about, or very briefly, is not quite in the archive yet. All right, so this second one is some mixed characteristic analog. And this is, as I said, it's not on the archive yet, but let me list the authors. Right, so this is joint with Hanlin Kai, Sung-Soo Lee, Lingshuan Ma, Carl Schweid, and myself, right? So, all right, so to do that, let me first give you a new interpretation of the F signature. All right. So still in characteristic P, one of the ideas here is, again, we saw this some in the talk yesterday by Jared, right? So if I think about Frobenius and I think about doing it over and over again, I might think about doing that in some sort of limiting fashion to get in this case, to the so-called perfection of the ring, okay? And the new interpretation we have is the following. All right, so there's two things over there that I haven't told you about. The first is this ideal I infinity. Right? So the first ingredient in the recipe is to look at the so-called degeneracy or non-splitting ideal for this perfection, right? So consider all the elements of the perfection so that they cannot possibly generate one of these free sum ends, right? So that the map that sends 1 to whatever that element is does not split and give me another free sum end, okay? The second one is what this lambda infinity is. right? And this is Falting's so-called normalized length. Okay, so appearing first in his papers on almost purity, right? And related to some of the perfectoid methods that have come up previously in Jared's talk. All right, so sort of let me end here with the mixed characteristic definition. So instead of assuming that you're in mixed characteristic, assume you're in, or you're in positive characteristic, assume you're in mixed characteristic. Instead of using rperf, what I'm going to do is the following. All right, so I'm going to start off and assume that this thing is complete and take a so-called Noether normalization of the ring. And the reason I do that is so that I have access again to some of these very nice, easy perfectoid rings that Jared mentioned before, namely, right, the ring A infinity 0. So this is, well, take my original ring, well, A, adjoin all of the pth roots of P in all the variables, and then P completed. Okay. When I do that, this ring is now perfectoid, and Bott and Schulze have given us something which will play the role of rperf over there on that board. Namely, I can take the perfectoidization or the relative perfectoidization over A infinity naught. All right. And the definition we've got now is that motivated by the right-hand board, you can take the Falting's normalized length of, again, this ring modulo the degeneracy ideal. Oh, no. All right, so in some sense, my talk here is just really an advertisement for these two really exciting new variants of F signature that have gained traction recently, right? People have been trying to get a mixed characteristic version of this thing for a while, right? And it's related to a lot of really, really interesting and exciting mathematics. What I didn't have time to tell you a lot about, but I'd be happy to talk to you about later, are also some of the applications that these invariants have, right? So just to mention a couple of them, one of them came up in terms of looking at finite quotients. So you can use these invariants to get bounds on the local Étale fundamental groups of singularities, for one. And especially this mixed characteristic picture here is very closely related to some very exciting work on splinter rings, right? Namely, a lot of this is building off of Andre's proof of the direct sum and theorem and corresponding advances in mixed characteristic algebraic geometry with applications towards the minimal model program named mixed characteristic, right? So we can talk more about that later if you like.